Hello friends, welcome to this YouTube channel. Today we are going to solve numerical problems from Electrical Machine 1 online mode semester examination paper held in March-April 2021 conducted by West Bengal State Council of Technical Education. Problem number 4b. A 25 kVA 2000 volt by 200 volt 50 Hz transformer offers its maximum efficiency at 80% of full load. Its per unit resistance and impedance are 0.012 and 0.05 respectively. We have to calculate its full load voltage regulation and efficiency at 0.8 lagging power factor. Let us first jot down the given data. Transformer rating S equals to 25 kilovolt ampere. Per unit resistance R per unit equals to 0.012. Per unit impedance Z per unit equals to 0.05. Given power factor cos phi 2 equals to 0.8 lagging. Therefore, sin phi 2 equals to 0.6. According to the problem statement, this transformer offers its maximum efficiency at 80% of full load. Therefore, we can write at maximum efficiency X equals to 80%, that is equal to 0.8. Let us now calculate per unit reactance. X per unit equals to root over Z per unit square minus R per unit square. Using values we get root over 0.05 square minus 0.012 square, that gives us 0.0485. Expression for voltage regulation at lagging power factor condition is R per unit cos phi 2 plus X per unit sin phi 2. Using values we get 0.012 into 0.8 plus 0.0485 into 0.6, that is equal to 0.0387 per unit or 3.87%. Expression for per unit resistance R per unit equals to P copper FL by S. Therefore, full load copper loss P copper FL equals to R per unit into S. Using values we get 0.012 into 25, that gives us 0.3 kilowatt. At maximum efficiency X equals to root over Pi by P copper FL. Therefore, expression of iron loss Pi equals to X square times P copper FL, that is equal to 0.8 square into 0.3, that gives us 0.192 kilowatt. Expression for full load efficiency eta FL equals to S cos phi 2 divided by S cos phi 2 plus Pi plus P copper FL. Using values we get 25 into 0.8 divided by 25 into 0.8 plus 0.192 plus 0.3, that gives us 0.9756 per unit or 97.56%. Problem number 5b. The test data obtained in a 5 kVA 200 volt by 400 volt 50 Hz transformer is given. During open circuit test, instruments were connected on low voltage side. Available data 200 volt, 0.7 ampere, 70 watt. During short circuit test, instruments were connected on high voltage side. Available data 15 volt, 10 ampere, 85 watt. We have to determine equivalent circuit parameters with respect to primary side. Let us first jot down the given data. Transformer rating S equals to 5 kVA, that is equal to 5000 volt ampere. Value of high voltage side voltage V1 equals to 400 volts. Value of low voltage side voltage V2 equals to 200 volts. Here we have used subscript 1 for high voltage side and subscript 2 for low voltage side. Let us now determine turns ratio. A equals to N1 is to N2, that is approximately equal to V1 is to V2. Using values we get 400 is to 200, that is equal to 2 is to 1. From open circuit test data we get no load loss P0 equals to 70 watt. No load current I0 equals to 0.7 ampere. Let us now determine no load resistance. R0 equals to V2 square divided by P0, that is equal to 200 square divided by 70, that gives us 571.4286 ohm. Let us now determine no load power factor. Cos phi 0 equals to P0 divided by V2 into I0. Using values we get 70 divided by 200 into 0.7, that gives us 0.5 lagging. Therefore, sin phi 0 equals to 0.866. Now we shall determine magnetizing component of no load current. Im equals to I0 sin phi 0, that is equal to 0.7 into 0.866, that gives us 0.6062 ampere. Now we shall determine no load reactance. X0 equals to V2 by Im, that is equal to 200 divided by 0.6062, that gives us 329.92 ohm. From short circuit test data we get short circuit loss PSC equals to 85 watt. Short circuit voltage VSC equals to 15 volts. Short circuit current ISC equals to 10 ampere. Equivalent resistance referred to high voltage side Req1 equals to PSC divided by ISC square, that is equal to 85 divided by 10 square, that gives us 0.85 ohm. Now we shall determine equivalent impedance referred to high voltage side. ZEQ1 equals to VSC divided by ISC, that is equal to 15 divided by 10, that gives us 1.5 ohm. Now we shall determine equivalent reactance referred to high voltage side. XEQ1 equals to root over ZEQ1 square minus REQ1 square, that is equal to root over 1.5 square minus 0.85 square, that gives us 1.2359 ohm. Let us now determine equivalent resistance referred to low voltage side. Req2 equals to Req1 by S square. Using values we get 0.85 by 2 square, that gives us 0.2125 ohm. Equivalent reactance referred to low voltage side, Xeq2 equals to Xeq1 divided by A square. Using values we get 1.2359 divided by 2 square, that is equal to 0.309 ohm. Here Req2, Xeq2, R0 and X0 are equivalent circuit parameters with respect to primary side. Problem number 8b. A 4-pole 220 volt lap wound DC shunt motor has 500 armature conductors. It takes 32 ampere from supply mains. The field winding and armature resistances are 110 ohm and 1 ohm respectively. The useful flux per pole is 30 milliweber. We have to determine the speed of the motor. Let us first jot down the given data. Terminal voltage V equals to 220 volts. Number of poles of the machine P equals to 4. Useful flux per pole phi equals to 30 milliweber, that is equal to 0.03 Weber. Given shunt field resistance RSH equals to 110 ohm. Number of armature conductors Z equals to 500. Armature resistance RA equals to 1 ohm. Line current IL equals to 32 ampere. For lap connected armature, number of parallel paths A equals to P, that is equal to 4 for this machine. Let us now calculate shunt field current. ISH equals to V by RSH. Using values we get 220 divided by 110, that gives us 2 ampere. Armature current IA equals to IL minus ISH, that is equal to 32 minus 2, that gives us 30 ampere. Expression for back EMF EB equals to V minus IA into RA. Here we are neglecting brush contact voltage drops. Using values we get EB equals to 220 minus 30 into 1, that gives us 190 volts. Again back EMF EB equals to phi ZNP divided by 60A. Therefore, expression for speed of the motor will be N equals to 60A EB divided by phi ZP. Using values we get 60 into 4 into 190 divided by 0.03 into 500 into 4. That gives us 760 RPM. Problem number 9b. A 4-pole lap wound long shunt DC compound generator supplies 25 kilowatt at a terminal voltage of 500 volts. The armature resistance is 0.03 ohm, series field resistance is 0.04 ohm and shunt field resistance is 200 ohm. We have to calculate the generated EMF. Let us first jot down the given data. Terminal voltage V equals to 500 volts. Output power PO equals to 25 kilowatt. Given shunt field resistance RSH equals to 200 ohm. Series field resistance RAC equals to 0.04 ohm. Armature resistance RA equals to 0.03 ohm. Let us now calculate shunt field current. ISH equals to V by RSH. Using values we get 500 divided by 200, that is equal to 2.5 ampere. Load current IL equals to PO divided by V, that is equal to 25 into 10 to the power 3 divided by 500, that is equal to 50 ampere. Expression for armature current IA equals to IL plus ISH, that is equal to 50 plus 2.5, that gives us 52.5 ampere. For long shunt compound generator, series field current IAC equals to IA, that is equal to 52.5 ampere. Neglecting brush contact voltage drops, we get expression for generated EMF E equals to V plus IARA plus IAC RAC. Using values, we get 500 plus 52.5 into 0.03 plus 52.5 into 0.04, that gives us 503.675 volts. So today we have solved numerical problems from Electrical Machine 1 semester examination paper held in March-April 2021, conducted by West Bengal State Council of Technical Education. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.